How's it going, everyone? I'm Jacob and this is Archimedes Tub, and today we're going to be discussing, is it feasible to make copper sulfate using electrolysis? So for my setup here, I have two copper electrodes. I have my DC power supply box here. This one goes up to 120 volts. And this is my other one. This one only goes to 30 volts. I'm not using that right now, but yeah, it's sitting there in the workstation. And so what I have here in my solution is a 1 molar magnesium sulfate solution. Yeah, and you can see already that I've been running that for a while now. This has been going off and on, just kind of like running this on my off days for like the past week. So yeah, so it's already got a little bit of a blue tinge going there. And I'll go ahead and tell you some of my observations from just like the little bit that I've been running it. On, I believe it would be my cathode here. We've been developing, I've noticed some like magnesium hydroxide byproduct forming on the negative terminal there. And obviously you have like a large amount of copper hydroxide being formed too, as to be expected. It's probably going to be the most dominant product of this reaction. So yeah, so been letting that run at approximately 120 volts, which is only at this moment translating to 18 to 19 watts, which really isn't a whole lot, I suppose. Of course, that's influenced by the conductivity of the solution, the distance between the electrodes, blah, blah, blah. And you can see I've got the electrodes tucked away in these pipettes here. Originally, I did have like some balloons secured to the ends of these pipettes, except I took those off. I was trying to catch like the oxygen and hydrogen gas that would be forming off of those, but I think a lot of it was just escaping back into the solution from the bottom, because of course you gotta have that openly available to the water, to the solution there, so I can conduct the electrical current. So yes, I've been running this off and on for the past couple of weeks whenever I had the time to sit there and monitor it, which isn't a whole lot, working full time and all that jazz. Not a big deal though. Do things as I can. So yeah, so we're gonna let this run for a few more hours today. I'm gonna filter off as much of the copper hydroxide as I can. I've been slowly collecting that, just as a useful byproduct. I'm not just gonna throw it away or whatever. But yeah, the focus of this video is whether I can, or whether it is efficient to use this method to try to make copper sulfate. Now, just thinking about it off the top of my head, not even doing any of the math on it, I'm gonna say it's probably not very favorable to the copper sulfate product. Like I said, we got the copper hydroxide byproduct as well as the magnesium hydroxide byproduct, which you could view the magnesium hydroxide as a good thing in a sense, because as that magnesium ions connect with the hydroxide ions, that leaves less of the magnesium ions in solution to convert back to the magnesium sulfate that's in the solution once I do try to crystallize that out of the solution. So yeah, and so obviously one of my biggest concerns purity wise is when I reduce the solution, just gonna, you know, heat off the water. That'd be the best way to get the crystals, you know, because well, one of my biggest concerns, what I was trying to say is the magnesium sulfate crystals that reform as the solution is being boiled off. So we would definitely have some magnesium sulfate contamination in our final product, which is unfortunate, but you know, such is life. But yeah, so what I'm really not worried about is having a whole lot of copper hydroxide contamination, because copper hydroxide, of course, is very negligibly soluble in water. So, of course, it's, you see at the bottom there how much is already precipitated out, and you know, it's not redissolving in the water, so I'll be able to just filter that off, easy peasy. You know, once I do decide to finally try to retrieve the final product, copper sulfate is, of course, soluble in water, so copper hydroxide contamination, not my biggest concern. My biggest concern would be the magnesium sulfate reforming as the solution is reduced. So yeah, so we'll cross that bridge when we get there. We'll see what it ends up looking like. Yeah, hopefully, you know, the longer I run it, of course, the more magnesium hydroxide byproduct that's going to be produced, which of course takes up hydroxide ions and magnesium ions. So as much magnesium as we can get out of the solution before we decide to reduce it to get the final product, you know, the better. But it was from just like my observations, magnesium hydroxide byproduct has production has been very minimal, so not a lot of faith in that being a key ingredient in reducing contamination. The final product with without the magnesium sulfate contamination, you know, just the equilibrium and all that, just it's just how it is. Haven't really looked into how I could push this more towards towards the copper sulfate product versus other byproducts. Because really the big thing is freeing up the sulfate ions to react with the copper ions in the solution versus reacting with the magnesium ions in solution, just reforming the magnesium sulfate that we used to make our solution there to begin with. So yeah, so I'm going to let this run for a good bit throughout the day, and then I'll, you know, filter off all the residual copper hydroxide, and then I'll use my hot plate sitting over there. I'll use that to reduce the solution and let the final product crystallize out. Should get some pretty blue crystals, and hopefully, you know, we'll see how that color is affected by the magnesium sulfate contamination in the final product, and I'll probably look into how to separate those out if there's any efficient way to do that. Unfortunately, they are both soluble in water, so that's unfortunate, at least for the purposes of this this particular experiment. I don't, just my hypothesis here, I don't believe this is a very viable method of making copper sulfate, but we will find that out towards the end of the video. So yeah, we will reconvene once I decide to reduce this. Okay, so while that is running, I took the liberty of drawing up this little table slash diagram thing here for us to sort of visualize what is actually happening in this reaction. Now, if you look on the right, you can see I drew up this image of an electrolytic cell. You can see that the cathode is connected to the negative terminal and the anode is connected to the positive terminal of our voltage source. This is the opposite of what it would be in a voltaic cell, where the cathode is the positive terminal and the anode is the negative terminal. But in both voltaic and electrolytic cells, oxidation occurs at the anode and reduction occurs at the cathode. So one of the biggest hurdles of my current setup is the competing reactions that take place when doing electrolysis in an aqueous solution. If you refer to the table on the left, we have, in this instance, competing reduction reactions between water and magnesium ions. And additionally, we have competing oxidation reactions between sulfate ions and copper ions. So, of course, we don't want our copper ions being reduced to solid copper, and we don't want our sulfate ions being reduced to sulfuric acid, or rather sulfate ions being oxidized to sulfuric acid. It would be an oxidation for the sulfate ion because it has a negative charge, which would be reduced, or rather increased or oxidized to the neutral charge of our sulfuric acid. While for copper, it would be a reduction to solid copper because we're reducing that positive charge of the copper ion to a neutral solid copper. So the reduction of water in this reaction is less favorable for us than the reduction of the magnesium ions to solid magnesium metal, because as the hydroxide ions are formed from the reduction of water, those hydroxide ions can sequester our copper ions and form our unwanted copper hydroxide, while the reduction of the magnesium ions to solid magnesium, not a big deal because we really don't need the magnesium ions for our final product. The production of the magnesium metal is just a happy side reaction that occurs. It doesn't really affect our final product, except in the fact that we don't have as many magnesium ions in the solution to reform magnesium sulfate, so that can push our final product towards copper sulfate. But more likely than not, we're going to see more of a production of sulfuric acid. So basically, this whole setup we got going here, it's not very favorable for the production of copper sulfate, as I, mentioned earlier before I sat down and really wrote this up. Because we have all these unwanted side reactions that are far more favorable to products we do not want. So yeah, like I said at the beginning of this video, we're probably not actually going to see a whole lot of copper sulfate final product. What we're going to be getting a lot of is copper hydroxide, magnesium sulfate reforming as the solution is reduced, and of course you got like you'll have water reforming too. So and then of course you'll have like your hydrogen gas, your oxygen gas. So basically this is not the most efficient or even slightly efficient way to produce copper sulfate. Not feasible, really. You would probably have more chance, a better chance of producing copper sulfate if you were to dissolve your magnesium sulfate into diethyl ether. It's one of the only other things that magnesium sulfate's really soluble in. And with diethyl ether, you really wouldn't have to worry too much about the production of hydroxide ions, depending on where you source your ether from. Of course, it's gonna have some water content in it, but definitely not as much as just like a straight up aqueous solution. So yeah, so you're gonna have, if you were to dissolve your magnesium sulfate in ether, you wouldn't have that competing reaction of the reduction of water, and you would end up, just off the top of my head, theoretically, I suppose, hypothetically, you would produce more copper sulfate than you would copper hydroxide. As far as like byproducts, I suppose in that case you would still have solid magnesium as a byproduct, and a minor amount of metal hydroxides, since you're not going to have 100% ether readily available. Most likely it's just not feasible physically, I suppose. Always going to have a little bit of water in there. So yeah, that's just on paper, this whole reaction setup thing we got going here, that's just the on paper view calculations. I didn't really put a whole lot of math into this. That's a whole nother can of worms for another video maybe. Yeah, so let's hop back over to the reaction and start filtering off that copper hydroxide and work on reducing the solution and see what kind of crystals we end up getting out of this thing. Alright, so now that we're back, I went ahead and instead of bothering with like actually trying to filter off all the copper hydroxide that had formed, I just decanted what I had out of this small beaker, this 500 ml beaker, into my larger 1 liter beaker. You can see it still has that blue tinge to it, so there's definitely still some copper hydroxide floating around in there, I'm sure. Such is life, it's gonna be a part of it. I wanted to show you something real quick. Part of what I was talking about earlier, here, at our cathode, you can kind of see some like grayish white formation there. I'm pretty sure that would be our magnesium, solid magnesium, that forms, like I was talking about earlier, showing you that chart. Don't quote me on that, just kind of guessing here, but just looking at it, you know, and based on what we talked about earlier, I would say that is definitely magnesium metal, but like I said, don't quote me on that. So yeah, so now we just have, get this bad boy to focus, we have our solution here sitting on our hot plate. Just gonna let that sit there and let it boil off. Looks like we got about 300 milliliters of liquid there. Hopefully it doesn't take too terribly long to boil off. I'm not gonna sit here and make you all watch that whole thing. We'll definitely come back to it in a bit. I just wanted to show you what was going on now, and also show you that the magnesium on the cathode there. So yeah, so we'll come back again once the solution is reduced down and we start getting our crystals. Alright y'all, here we are at the conclusion of this video. Here is the final product. Is it copper hydroxide? Is it copper sulfate? Who knows? Not really what we were going for here, you know, besides, I guess, to just prove my point that I made at the beginning of the video, that this is definitely not the best way to go about making copper sulfate. There's too many byproducts, which leads to too much contamination in the final product. Really, this was more so just a learning / teaching experience. Maybe the copper sulfate was actually the friends we made along the way. But yeah, so, you know, gives you a little idea of the challenges of using aqueous solutions for electrochemical reactions. Can definitely be more of a hindrance than a help. Now something to note, I could take all that copper hydroxide I made, treat it with sulfuric acid, and boom, copper sulfate, but just using electrolysis to directly make copper sulfate, not really the move. So yeah, this has been, you know, fun, educational, I would say, hopefully. At least for me, hopefully it was the same for y'all. You know, if you take anything away from this, I hope it's just that even if you're not particularly doing anything useful, hopefully you're having fun, because that's, you know, I would say 3/4 of the science is having fun while you're doing it. Otherwise, it's, you know, just a job. But, you know, in this case, I hope it's more of a hobby. Definitely more of a hobby for me. So yeah, so if you like the video, you want to see more, feel free to like and subscribe. Turn on notifications if you want to. Hopefully I'm going to be putting stuff out more regularly again. Life's just been pretty busy. I'm sure y'all know how it is. And actually, while I got you here, check out the cathode again. Look at how white it is now that it's all like dried and stuff. Definitely, let's see if I can't turn the light over this way, get a better view here, but I would definitely lean towards that being some magnesium metal mixed up in that, obviously a little copper hydroxide contamination, hence the blue color in there in some parts. But yeah, so overall, hope everyone had fun, and I will see you next video.